Simple things can be beautiful. This entire effect is based on a rule that says when two particles are close enough to each other, connect them with a line. Define a rule, apply that to a blueprint, and create many particle objects using that blueprint. That's how you build a particle system, one of the main pillars of creative coding. This is so-called constellations effect because it looks like diagrams of star patterns. It was made famous by the Particles.js library, and today I will show you how to make it completely from scratch with JavaScript. No frameworks and no libraries. All you need is a code editor and a web browser. This class is for beginners. A basic knowledge of HTML, CSS and JavaScript is needed to get the maximum value. In index.html, I created a simple generic web page. I linked my CSS style sheet and JavaScript file, and I created HTML5 canvas element with an ID of canvas1. Today we will use fundamental programming principles and techniques, functions, arrays, and for loops, and step by step we will add more and more features to build our effect, while making sure we understand every line of code. I could have used a library, but without full understanding of how the code works, we would always be dependent on that library and its features, and what they do and don't allow us to do. Being able to write and fully understand the code gives us an ability to modify and enhance this effect in many different ways, and we can use it in many different types of projects. In style CSS, I gave canvas a black background. I position it and I define a few basic global reset rules to make sure our web page looks the same in different browsers. I will split the logic in 4 main code blocks. Project setup here. Particle class will contain a blueprint to create individual particle objects. Effect class will be the brain of our code base. It will manage all particles, and animate function will run over and over, updating and redrawing the shapes to create animation. I point the JavaScript towards canvas element we created in index.html using getElementById. CTX, shortcut for context, will be that canvas variable .getContext, and I pass it 2D to create an instance of something called canvas rendering context 2D, which is basically a built-in object that contains all properties and methods we will use for drawing today. I take canvas from line 2 again, and I set its width to the full width of the browser window. Canvas height will be the same as the height of the browser window. I will console log CTX, and we can see that canvas rendering context to the object I mentioned before. If I open it, we can see some of its properties. For example, we see that the default fill style is set to black. I can take CTX variable and access this fill style property like this, and I can override it to a different color if I want to. I can also call built-in fill rectangle method. So all canvas properties sit here. If I scroll down and I open this area, I can see all built-in drawing methods. Fill rectangle method is here. I pass it 4 arguments, x and y coordinates of the top left corner of the rectangle, and its width and height. Because I set my fill style to white, we are drawing a white rectangle of this size at these coordinates. I can move it around by adjusting the coordinate values. I always do a small test like this just to check if our canvas was set up correctly and that everything is working. All is good, so I can delete this. Click the like if you're getting any value and you want more creative coding tutorials. The main effect class is the brain of our code base. It will store all our custom settings and helper methods we will need today. The main thing it needs is the width and height of the available canvas area, because we need to make sure we draw our shapes only within the canvas area and not somewhere off screen. It will expect a reference to canvas from line 2 as an argument, and inside we convert it into a class property. I create this.width property, the width of the effect, and it will be equal to the width of canvas. So we are actually pointing to line 4 here. Same for height. Particle class will contain a blueprint to create, draw, and update individual particle objects. We will define what particles look like and how they behave here. I want to keep object-oriented code structure, and I want to do good coding practices to keep our classes modular and as independent of the surrounding code as possible. I want particles to see properties on the main effect class, so every particle will expect a reference pointing to the main effect object, like this. We are not creating copies of the effect here. We are just pointing to that same effect class from multiple places when we create multiple particles a bit later. From that reference, pointing to the main effect class, I can access its width property, and I can say that horizontal x-coordinate will be a random number between 0 and effect width. Vertical coordinate will be a random value between 0 and effect height. Particles will be circular, so radius of these circles will be, for example, 15 pixels for now. Draw method will contain some drawing code. It will define what each particle looks like. I want them to look like simple circles. To keep this modular, instead of pulling CTX from line 3 directly into my class, this method will expect context as an argument. To draw a circle on canvas, we start by calling beginPath to tell JavaScript we want to start drawing a new shape. Built-in arc method, and we pass it x and y coordinates of the center point of the circle, its radius, start angle of 0 radians, and end angle of math.pi times 2 to give us a full circular arc. Arc method just defines a path, it doesn't actually render anything. To render our path on canvas, we can either fill it with color, or we can just outline it with stroke method. I call fill to draw the circle. Particles will be stored here on the main effect class in an array. This.particles will first start as an empty array. Number of particles will be, for example, 20 to start with. I define a helper method here called createParticles. This method will run just once to initialize the effect and create 20 particle objects. Inside, I create a for loop. It will run 20 times. Every time it runs, it takes this.particles array from line 27 and it will call built-in pushArray method on it. Push method takes whatever we pass to it and it pushes that to the end of the array. I pass it a new particle, like this. The new keyword is a special command in JavaScript. It will look for a class with the name particle and it will trigger its constructor method to create one instance of that class. On line 9, I can see that particle class constructor expects effect as an argument, a reference to this entire effect class, because we want to have access to all these properties and methods that sit on the main effect object from inside particle objects. Because here we are inside that effect class, I just pass it this keyword, which in this area refers to the entire effect object. So as we just said, when the new keyword is called, class constructor is triggered, and the code inside is executed line by line to create one new object. We can actually put any code in here. I want 20 particles to be automatically created when I create an instance of effect class, when this constructor method runs. So I say this.createParticles in here, triggering this method. We will need another helper method to handle all particles. I take this.particles array from line 27, which now contains 20 particle objects, and I call built-in array for each method. For each method executes a provided function once for each array element. We need to assign each array element a variable name, so I will call them particle. And for each particle object in particles array, I want to call its associated draw method from line 15. I can see that it expects context as an argument to specify which canvas we want to draw on, so I pass it context like this. And this value will be coming from here, because handle particles will also expect context. We will finish this in a second. First, I need to create an instance of our main effect class, so a custom variable I call, for example, effect will be equal to new effect. Again, the new keyword will find the associated constructor and it will create one new blank JavaScript object and it will assign it properties based on the blueprint inside. It will execute all the code line by line. For that to happen, I need to pass it canvas as an argument, so I pass it canvas from line 2. Remember that we are doing it this way to keep our classes self-contained and less dependent on their surrounding code, on where they sit in our codebase, on their so-called lexical scope. I console log this effect variable from line 42. In console I can see it has width and height, and because line 29 was automatically triggered when we created an instance of effect class, now it also contains particle array with 20 objects inside. Important thing here is to check one of them and make sure all its properties have values and we don't have any none or undefined here, which would mean we have a problem somewhere in our particle blueprint in the area where these values are calculated. All is good here. So far we know all our code is working. It's good to test your code step by step like this to catch any potential issues in time. Now I can take this effect variable and I call handle particles from it. It expects context as an argument, so I pass it ctx from line 3. I don't see anything on canvas, but if you remember, the default fill style color is black. We have black shapes on a black background. I can define fill style in here and set it to, for example, red. Nice, we are drawing 20 circular red particles. This draw method will run 60 times per second for each of our 20 particle objects. For performance reasons, we want to access and override canvas state as little as possible, so instead of running this line of code over and over so often, since all our particles are the same color at this stage, I can delete this and instead I will define fill style here. This line of code will run just once on the initial page load. It's important to think about these things when structuring our code. Try to change canvas state as little as possible to improve performance of your animation code bases. So this is how you create a basic particle system as an object-oriented code base. We can create many different effects and animations from this. If you want, you can save a copy of the code at this stage in a different folder and use it for other creative coding experiments in the future. Today we will turn this into animated bouncing balls first and then into beautiful particles constellations effect. Sometimes we can't just declare fill style once. For example, maybe I want each particle to have a different color. In that case, I have to define fill style in here and change this setting every time we are about to draw a new particle. HSL color declaration is probably the most useful way to declare colors if you want to animate them or control them with code in any way. It contains 3 values for hue, saturation and lightness, where hue is a degree on a color wheel. Saturation goes from 0, grayscale, to 100% fully saturated, and lightness at 50% means the color is not affected by light or dark at all. We can easily cycle through the entire color spectrum by increasing hue value from 0 to 360. I can do many different things here. I replace hue with a variable, and I can use this.x here, which means the degree on the color wheel starts from 0 for particles by the left edge of canvas, and it increases as we travel right. I can scale it by half, for example. I increase the number of particles to make it more obvious what's happening. We can scale the value here. We can set a specific value, or I can randomize it. To get the entire color spectrum, we can do a random value between 0 and 360. So this is how I can connect it to the horizontal x coordinate. I can also call stroke here, so we are filling the shape and we are highlighting it. By default, stroke style is black. I can change it like this. I can also change line width like this. I want the particles to be fully visible, not partially hidden behind the edges of canvas. This will be especially important when we make them bounce off the edges in a minute. I need to declare radius first before I can use it for these calculations, because this code is read line by line from top to bottom. So I want the randomized horizontal range to start from here, so this.radius, because we are dealing with the center points of these circles. Now it goes from here, somewhere here. We need to reduce that range by radius from both sides actually. So from here, the random range is width minus radius times 2. It needs to be in brackets to give us the correct range of values. Now, if I refresh the page, you can see that horizontally the circles are fully visible. I do the same thing vertically. We want a range from here to here, so from radius to height minus radius times 2. Now all circles are fully visible. I might need to adjust my screen recording area a bit to really show you. But if you are coding along, you can see yourself that it did it. It will work even when we increase radius to 50 pixels. Or random radius between 0 and 50, between 1 and 41, Circles that are less than 2 pixels will be barely visible anyway. We can animate the particles and make them bounce around. Each particle will have update method, which will run over and over for every animation frame, and it will define particles' motion and behavior. Let's start by just making them all move to the right by 1 pixel per frame. If I call update from down here, it will trigger update just once, so there is no movement. We need to call update and draw over and over to create animation, so I will call handle particles from inside animate loop. We call animate, some code runs, and we call request animation frame and we pass it animate, the name of its parent method, to create animation loop. Request animation frame will automatically adjust to the screen refresh rate, so for most of us it will run this animation at 60 frames per second. We see these trails, it's old paint. We can delete previous animation frames by clearing the entire canvas between each animation step. Built-in clear rectangle method from coordinates 0, 0 to width and height of canvas. Now we see only the current animation frame. I can also declare the speed as a separate property. Vx, velocity on the horizontal x-axis, is +1, 1 pixel to the right per animation frame. And I increase x by Vx here. We get the same result, but now we can flip it and make them bounce, because I can say if x is more than width, set Vx to its opposite value. If Vx is currently +1, it will give us -1, because +1 times -1 is -1. We can also do it for the opposite side using the same line of code. If x is less than 0, again multiply the current Vx times -1, so particles are moving left, their Vx is -1, they reach the left edge and -1 times -1 is +1, it will flip the direction again. This is a great line of code because it's so simple and it will make the particles endlessly bounce left and right. Because these are circles, x and y coordinates define their center points, so they only bounce when the center point reaches left and right edge. If I want my particle circles to bounce as soon as the right edge of particle circle touches the edge of canvas area, I have to account for the radius here and here, like this. It will work even when each particle has a different randomized horizontal speed. For example, a random speed between 0 and 4 pixels per frame. Or if we want them to start moving both left and right, I want some of them to have plus, some minus speed, so a random speed between -2 and +2. I do the same for Vy, velocity on the vertical y-axis. If I apply Vy to this .y, combination of randomized positive or negative vertical and horizontal speeds makes particles move in all possible directions to all sides. And we will make them also bounce vertically by copying this line and adjusting it. If this .y is more than height minus radius, so on the bottom, or when this .y is less than 0, when it's on the top, make it bounce by flipping velocity y to its opposite value. And this is how you do bouncing. Again, there are so many things that can be done with this. These are extremely useful code bases that allow us to make thousands of different particle effects. Feel free to save this version of the codebase in a separate folder, so you have a quick basic boilerplate codebase ready for your future creative coding experiments, and you don't always have to write this base code structure again. If you observe one particle and follow it around as it moves, you will notice that its color cycles through the color spectrum based on its current horizontal coordinate, because of the code we wrote on line 19. We can achieve the same effect but have more control over the direction of the colors and over individual color breakpoints if we use built-in create linear gradient method. We can just declare it up here on the first page load. Create linear gradient method expects 4 arguments to define the direction of the gradient. I want it to start from the top left corner, coordinates 0, 0, and I want it to end at the bottom right corner, coordinates canvas width and canvas height. The gradient will be drawn along a line connecting these 2 points. I take that custom gradient variable and I call built-in addColorStop method. It expects 2 arguments, offset and color. Offset is 0 at the beginning of the gradient, Offset 1 is the end of the gradient. I want 3 breakpoints. We start at offset 0 with white, 0.5 in the middle will be magenta, and end will be blue. I delete this fill style declaration and instead I assign fill style to this gradient variable we just created. As you can see, we go from coordinates 0, 0, top left corner, starting from white, through magenta in the middle, all the way to blue in the bottom right corner, where the gradient ends. Nice! There is also create radial gradient method, in case you want gradients in circles. I can change the size of my particles by changing the radius value. I can slow them down. Maybe a random speed between -0.5 and +0.5 pixels per animation frame. This concludes the beginner version of this class. Now we will take it to the next level and we will use a few common and extremely useful creative coding techniques to turn this bouncing balls effect into the famous particles constellations effect. Only we will not be using libraries. We wrote this codebase line by line and we will fully understand it, which means we can do with it anything we want. For example, I have another class where I made the particles fill letter shapes as we dynamically type that text into an input field. But that's a bit more advanced class compared to this one. Let's cover the basics to make sure we understand exactly how this effect works. Constellations effect connects particles that are close enough to each other with lines. Let's start with that. I create a custom method I call, for example, connect particles. We only want to connect particles that are 100 pixels apart or less from each other. Max distance is 100 pixels. I want to cycle over the entire particles array over all the elements one by one, so we create a for loop. This bit is important. I want to compare every particle inside this .particles array from line 43 against every other particle object in that same array, so that I can calculate their distance and check if they are less than 100 pixels apart. To do that, I need to use nested for loops, a loop inside of another loop. Basically, I want to cycle over the entire particles array, and for each of those particles, I will run over the same array again to compare each particle against all other particles in that array. I don't actually have to cycle from 0 here in the inner for loop, because some pairs of particles will have already been compared in the previous runs of these loops. So the inner index I called B will start from index A, and it will continue from there. It will not start all the way from the beginning, from index 0, because that would mean we are comparing pairs of particles we already compared. Don't worry if you can't visualize that. It will make more sense if you use this technique more often. All you need to understand here is that structuring two nested for loops in this way allows me to compare each particle object in this .particles array against all other particles in that same array. We are always comparing two particles at the time until we compared all of them, until we covered all particle pairs. We will always be comparing particle object with index A in the array against another particle object with index B in the same array. For each loop, we have to do the following. We have two objects, particle A and particle B, 2 points in a 2D space somewhere on canvas. We want to calculate the distance between these 2 points. Let's say particle A is here and particle B is here. We want to know the distance between them. So how to calculate the distance between 2 points in a 2D space? This is a very important coding technique if you want to write code for physics simulations, games, or creative coding projects. To get this distance value, we need to imagine there is a right triangle in between them. This will work regardless of where, in which position relative to each other, particle A and particle B are. We calculate dx, the distance between particle A and particle B on the horizontal x-axis. We calculate dy, the distance between particle A and particle B on the vertical y-axis. We have this side of the triangle. We also know this side. And we know this is a right angle, 90 degrees. Knowing all of this, we can use Pythagoras theorem formula to calculate hypotenuse, the longest side of the right triangle, which is also the actual distance between these 2 points. We can calculate it using Pythagoras theorem formula, which would be square root of dx squared plus dy squared. And since we are using JavaScript for this codebase, we can also use built-in math.hypotenuse method, which will calculate that value for us as well. We just need to pass it dx and dy, this side and this side, and it will give us hypotenuse, the distance between the 2 points. Understanding this concept is extremely important because it can be used for so many different types of projects. I use it a lot when writing code for my 2D games, for example. We know the distance now, so if distance is less than max distance, if particle A and particle B are closer to each other than 100 pixels, we will draw a line from particle A to particle B, connecting them together. I'm still console logging my CTX variable, so if I open the browser console and I scroll down here, I can see built-in line2 and move2 methods, which we will now use to connect our particles with lines. Okay, so in this area, we know particles are close together, so we want to draw a line. We start a new path by calling beginPath method. Move2 method will define starting x and y coordinates of the line, so we pass it x and y coordinates of particle A. Line2 method will set the next point along a path if we are drawing a more complex shape, but in this case it will define just the ending coordinates of the line, so I pass it x and y coordinates of particle B. Same as arc method, move2 and line2 methods just set the path. To actually render it on canvas, we have to stroke it or we have to fill that shape with color. We have just a simple line here, so I call built-in stroke method to draw that line. So again, we want to connect particles that are close enough with lines. We compare every particle against every other particle in the same array using nested for loops. We calculate dx and dy, and from that we calculate hypotenuse to give us the distance between particle A and particle B. If distance is less than 100 pixels, we draw a line from particle A to particle B. I call connect particles from inside handle particles method here. We are drawing on canvas inside this method and we are using context here, so connect particles will expect context as an argument. And here I take this context argument and I pass it along. Nice, we are drawing the lines. But as we said before, by default, the stroke style is set to black. I go up here and I set stroke style to white. Perfect. I want the lines to be behind particles. We are drawing everything on the same single canvas element, which means that whatever is drawn first is behind whatever is drawn later. What comes last is drawn on top. I put the lines behind particles by drawing the lines first and particles after. We built Constellations effect with no frameworks and no libraries. Well done if you followed this far. There are many ways to improve this. If you look at the lines, they appear and disappear instantly as particles get in and out of range of each other. I would like the transitions to be more gradual to get a smoother effect. We could, for example, connect opacity of the lines to the distance between the particles. If particles are right on top of each other, lines are fully visible. As the particles get further apart, we gradually reduce opacity of the line until the opacity is 0 and the line becomes fully invisible at the exact same point when particle distance reaches 100 pixels. On canvas, we can declare opacity by defining global alpha property, where 0 is invisible and 1 is fully visible. I want this opacity value to be 1 when particle distance is 0, when particles are close to each other. And I want opacity to be 0 when particles are 100 pixels apart. And of course I want to spread the values in between into this range. When particles are 50 pixels apart, I want opacity to be 0.5. When particles are 20 pixels apart, I want opacity to be 0.8, and so on. I do this by using a formula like this. I want opacity to be the ratio between the current distance and the max distance. So, for example, when the current distance is 50 pixels and max distance is 100, it will always be 100, 50 divided by 100 is 0.5. when the current distance between particle A and particle B is 30 pixels, 30 divided by 100 is 0.3. I hope this makes sense. I also want to flip this. When particles are near, distance is a low value. I want opacity to be closer to 1, to the maximum highest range. When particles are far apart, distance is a high value, close to the maximum 100. At that point, I want opacity to be close to 0, close to its lowest point. I can do that by taking the maximum value. We know that the distance divided by max distance will never be more than 1, because this code block runs only when distance is less than max distance. And when you divide lower number by the higher number, you can never get more than 1. For that reason, I can take maximum possible opacity value of 1 and use it like this. Max value minus the ratio between the current distance and the max distance. We flipped it, and now let's say the current distance is 30 pixels. 30 divided by 100 is 0.3, 1 minus 0.3 is 0.7. When the distance is 30, opacity is 0.7. This might be challenging to visualize for some of us. It's quite advanced actually for beginners, but as with other techniques we used today, it becomes easier if you use it more often. All we need to know here is that I'm using this line of code to convert the current distance between particles to a range between 0 and 1, but I'm flipping it, where high distance value is low opacity and low distance value is high opacity. Now I can use this dynamic opacity value as my global alpha property. Global alpha, same as fill style, stroke style, and other canvas settings, change the state of the entire canvas. Which means that once we declare this value, once we set this canvas setting to a specific value, all shapes drawn after this will get that setting. I only want this particular opacity value to affect this particular line shape, only these few lines of drawing code. So I wrap this code block in built-in save and restore canvas methods. Save method will save all canvas settings. We can make any changes we want in here, and those changes will affect only this shape. Then we call restore and we reset canvas state back to what it was at this point where we called save. In this case, we are returning global alpha back to its default value. And now we have a visual representation of what we just talked about. When particles are close, lines connecting them have higher opacity. As particles move further apart, the lines get gradually more and more invisible until they disappear completely, at the point when particles reach maximum distance. I can remove the stroke on particle circles. It will also improve performance of our code base because stroking all these circles is performance expensive. I set the radius to a random value between 2 and 7 pixels. Now, when the particles are smaller, we can better see that when particles are very close to each other, the lines are drawn at full opacity. They are fully visible. We can also make the particles react to mouse. We can push them around and add some physics to make it more dynamic and interactive. We can also experiment with other movement patterns. Right now, the particles are basically just simple bouncing balls. Join me in the advanced section where we implement all these features and we will play with this codebase in many different ways. Well done on completing the project. If you want more, Part 2 of this class is all about creative coding experiments. See you there!